and do basically what I had on the board the other day and write different subshells of orbitals. So I have 1s, and then I have 2s, 2p, and then I have 3s, 3p, 3d, and these aren't spaced correctly, but we're increasing energy. And then I have 4s, 4p, 4d, and 4f. And I'm not going to belabor this, but anytime it's an S, it's going to have one box, so we can put 2 electrons. Anytime it has a P, I'm going to go ahead and do it this way. I have 3 boxes, I can put 2 electrons in each, so I max out at 6 electrons. I pick up a D type at principal energy level N is equal to 3, and then here we go. That wasn't going to work. All right, I need to get 5 boxes out of this. I'm just going to put it back and join my boxes. Okay, so 2 electrons, 2 times 5 would make 10 electrons, maxing out. So I got 7 electrons, or so, excuse me, 7 orbitals. Boxes are orbitals, 5, 6, 7. Okay, so that's kind of generally speaking what we have. So this topic actually is, I kind of alluded to it on Friday. We're going to find homes for electrons. And as we find homes for electrons, that's what we call the electron configuration for that atom, for that ion. How the electrons are hanging out. And we talked about ground state and excited state, and we're actually going to do the whole ground state thing. So as I've drawn this energy diagram, we'll find homes for the lowest energy, and it's called Aufbau. In German means building up. We'll kind of fill an entire subshell and we'll kind of build up with regard to energy. And I already told you I'm going to have to kind of, and I think it's coming up, reorder a few of these subshells with regard to their relative energies. In order to know which subshell is going to have the lowest energy, we can use what's called the lowest N plus L rule. So if I go over next to, grab a different color, next to each one of those subshells, I could write an N plus L value. So it's going to be in purple, N plus L. Now, in order for this to make sense, we need to kind of go to something I cover in general chemistry, that if you have an S, a P, a D, or an F, we can give it an L value of 0, 1, 2, and 3. So you kind of need to know that. So when it comes down here to 1s, the N value is 1, and the L value is 0. Okay, so 1 plus 0 is 1. Here we have 2 plus 0, I'm liking 2. Here we have 2 plus 1, I'm liking 3. Here we have 3 plus 0, another 3. Here we have 3 plus 1, I'm liking 4. Here we have 3 plus 2, 5. Here we have 4 plus 0, 4. Okay. And here we have 4 plus 1, 5. And here we have 4 plus 2, 6. Nope. Yeah. And then here we have 4 plus 3 for 7. So whatever that N plus L value is giving you a sense for relative energies. And I told you that I'm going to have to unscramble something. And that unscrambling actually is going to come right here. This guy, we're going to see here in a minute, goes right here with regard to energy. So I lied just a little bit, not too bad. In other words, the 3D subshell, these 5 orbitals, actually have more energy than the 4s. That's okay. So you don't have to know how to unscramble them. I've actually got something called the arrow diagram that should help us. So in the lowest N plus L rule, N is the principal energy level, and L is a value for the orbital. And I kind of showed you the corresponding numbers. And S is 0, P is 1. These are actually what we call L numeric values, or I call them L numeric values. All right. Oh, I do have my slides. So when we talk about, well, quantum mechanics and quantum physics kind of hurts my brain and all that, but we are coming up with what's called, along the same line, we'll call quantum numbers, corresponding to the S, P, D, and F. And we don't have to worry about G and H as electrons are hanging out around an atom or an ion in their ground state. Okay. Well, I just kind of got ahead of myself, didn't I? So when we go here for this subshell, that's 1 plus 0 or 1. A 2s is 2 plus 0 or 2. 2p is 2 plus 1 or 3. Okay, 3s is 3 plus 0 or 3. They're both 3, aren't they? 3p is 4. 3d is 5. Okay. All right. So I already kind of been alluding to this. Should have looked over my slide more carefully. But we actually are going to find homes for electrons in the lowest energy, and then we're going to the next energy, and the next energy, and the next energy. Completely fill a subshell if it's following the rules. That will know how we're going to kind of build our electron configurations. Okay, now here's one for you. If you happen to have, which we do, like here, right here, we have the same n plus L value for 2 subshells. You go with the lowest n first. Right? Sounds good. And what this is saying in bold there is, it says, don't forget that for any, choose a different color. For any S-type subshell, we can only accommodate 2 electrons. I'm kind of a visual person that way. For any P-type, we can accommodate 6. For any D-type, we can accommodate 10. And for any F-type, we can accommodate 14. So kind of remember how that works. And kind of the plus, if we have 2 electrons in the same orbital, if they're sharing the same box, they have to have opposite spins. I mentioned the word Aufbau a minute ago. It's a German word meaning kind of building up. And so this is so exciting. So for instance, if we know, I'll use a periodic table to make my point here. If we know how the electrons are configured around a carbon atom, and if it's neutral, has 6 protons, if it's neutral, has 6 electrons, then actually the electron configuration for a nitrogen atom, for 7 electrons, just 1 electron away. So you're like, dude, you got carbon, just add an electron. Now you got nitrogen. Okay, so it is so cool. So I think relatively straightforward. No calculator needed for this part of the material. Okay. All right. So hold that thought. I'm going to come back to what's called an arrow diagram to kind of show you how do you know which energy level is going to go next. But before that, I need to talk about the 2 ways that we say how electrons are configured around an atom or an ion. We can represent them either with box and arrow notation. Now, as I've been doing this is box, and I'll show you arrow. This would be box and arrow notation. If I go ahead and put 2 electrons in there, of course I'm talking about something, and it's a neutral atom. 2 electrons, you're talking about helium. Okay, so that's the box and arrow notation of the way those 2 electrons around a neutral helium atom are hanging out. The other one, and I'm going to show you this, but I've been getting ahead of myself all lecture so far. Why not go ahead and do it one more time? So alternatively, it's called spectroscopic notation. If I wanted to show those 2 electrons in the 1s, I would say 1s for what subshell they're in, and I would put a superscript 2 for how many electrons there are. So these are the 2, what we say, notations for to say how those 2 electrons are hanging out. Box and arrow and spectroscopic. Oh, by the way, box and arrow, your textbook uses, I think, circles. And so maybe, I don't know, this is called an orbital diagram, what Tro uses. And spectroscopic notation is what he calls electron configuration. Okay, so let's start with box and arrow. Okay, So we've been talking about this, that the boxes in light of this subject mean the orbitals. And you guys did some homework where you guys showed me s orbitals are spherical, p orbitals are dumbbell shaped, and then d's and f's are just strange. Well, f's are very strange. Now one thing about it, and maybe I'll go ahead and try to kind of, well, yeah, I'll try to fix what I have up here. One of the things I see students that they do wrong about this sort of notation, the box and arrow notation, is they don't say what that box is or what those set of boxes are. So you need to get in the habit of, on your homework and on a test, telling me, for instance, this is 1s. So you write it under that one orbital. You need to tell me on your homework or test that that is actually 2p. I can't guess. Okay, this is 3d. Don't make me guess or you won't get full credit. This is 4f. So when it says each subshell should be labeled, that's what I mean. Those are those degenerate orbitals in the same subshell. The arrows are going to represent electrons, and we already talked about if you have 2 electrons in one orbital, it's maxed out, and they have to have different quantum numbers. They have to be unique. So we're going to go with a plus spin and a minus spin, plus 1/2 and a minus 1/2. This last one's a little debatable, but I guess I'm fine with it. If you happen to have what we call an unpaired electron, an electron that has its own room, go with the up arrow, not the down arrow. Be a rebel. No, don't be a rebel. Okay, so let's see what this looks like. And you've already seen my attempt at boxes is not great. So 1 electron associated with the hydrogen is going to go right there. 2 electrons associated with the helium. And I know you've kind of asked about ions. When we have a species that has a certain number of protons, but not the same number of electrons, and we'll get to that. As it is right now, we're just going with where the number of electrons is equal to the number of protons. Lithium atomic number 3 looks like this. Notice we're going to fill this guy first, then we'll put the third one over here. Beryllium atomic number 4 looks like that. Boron atomic number 5. And then we get exciting with carbon, with atomic number 6, with 6 electrons. And I think I mentioned this the other day, that they're going to spread out, because I kind of picked on carbon. We have 6 electrons we can find homes for. Of course, they're going to go 1s, 2s. They're going to start filling that 2p, but they're going to spread out. And I have a name for that, I think, on the next slide. That's actually called Kuhn's rule. Notice they're spread out, but they have the same spin. Okay, so carbon is the first time that comes into play, where we can accommodate 6 electrons there, and we only need homes for 2 electrons, and they're going to get their own room. Okay, so this kind of gets to paired electrons versus unpaired electrons. So this is an example of paired electrons. And when carbon kind of finishes up with 1 electron in the 2p subshell, that is an unpaired electron. All right. So we pick up after carbon, we have atomic number 7, nitrogen. 7 electrons look like this. 2 there, 2 here. So I need 3 more, and they're going to actually all be unpaired in their own little room. With a positive spin. So now with oxygen, we have to go back and start putting, remember we can accommodate 6 electrons in the 2p, so we haven't maxed out yet. So we're going to go ahead and buddy up in that first room. And then for fluorine, we go ahead and buddy up in 2 rooms. Just kind of like minding your own house. All right, and then neon. And as you may already be kind of familiar, neon then reaches the last group in the periodic table. Those are especially stable. They're not called inert gases for nothing. Inert means they don't like to react with other things. And the reason is because reactivity is a result of atoms trying to go ahead and get what the rare gases already have. Sometimes this is called a complete octet. Oct meaning 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So there we go. So we're going to do those same elements up through neon with spectroscopic notation. The box and arrow kind of reminds me of hand cramp sometimes. It gets my hand cramped drawing those boxes, which I'm not very good at. But this notation is, I think, easier, but you need to be able to do both types of notation. So in this sort of notation, as I did with helium, we're going to actually do we're going to write the subshell that the electrons are in, and we're going to use a superscript to the upper right-hand corner as to how many electrons are in that subshell. And it is a superscript meaning small. So it's a small number up there. This is small. This is big, which is part of the principal energy level. Okay. So with this sort of notation, we're going to talk more about this. Oh, wait a minute. Yeah. So what's handy sometimes is to basically come out of how the electrons are configured and then to reorder them in order of increasing n. And I'll show you how we do that, and I'll show you why we would want to do that. All right, here we go. So you're going to hear me kind of do it this way. Hydrogen, 1s1, where when I said 1s, 1 is the principal energy level, or my first one is anyway, 1s is the subshell, and the 1 is how many electrons there. So helium is 1s2. Of course, lithium, we need to go ahead and go into the next subshell because we can only put any two electrons, or an S-type subshell like 1s can only accommodate 2 electrons. So 1s2, 2s1. Don't forget those little numbers, those superscripts, number of electrons are little. Beryllium, 4 electrons, 1s2, 2s2. And here's a good example. If you're doing this sort of notation, spectroscopic notation, if you want to know where you are, just add up the superscripts. So I know I have 4 electrons represented. So now I go to boron, 1s2, 2s2, 2p1, 5 electrons. And this actually is the first example where we kind of lose some information with this sort of notation. So we know that Hund's rule says that carbon actually peters out with 2 electrons in these 3 degenerate equal energy orbitals of 2p, and they spread out. But that's not our problem. 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. So it just kind of keeps building on it. Oxygen, 1s2, 2s2, 2p4. Superscripts add up to 8, which is nice. Fluorine, 1s2, 2s2, 2p5. Atomic number 7. Wait, sorry, atomic number 9. Okay, atomic number 10, neon. So 1s2, 2s2, 2p6. So that kind of, what we say, rare gas configuration, that complete octet, you can see by these 8 electrons right here. Sometimes this is called, all rare gases have this pattern where on the principal or the highest energy level, you're going to have what we say NS2, NP6. Oops, sorry, drat. NS2, NP6. That's the generic formula for a rare gas. Okay, so I can promise you your test a week from tomorrow is going to have this arrow diagram. So you might as well figure out how to draw it. And then when you draw it on your test, you can use it. Okay, so nothing like having the creative tool that you can use. So I think I'll go ahead and create the arrow diagram here too. It just seems like I have my builds, but oh, I'm getting rid of the evidence. All right. And the arrow diagram will show you how we move the orbitals. So, and the arrow diagram looks like this, where you write subshells. You write for n is equal to 1, you only have one type of subshell. N is equal to 2, you have 2s, 2p. And I'm going to make these columns. N is equal to 3, I have 3s, 3p, 3d. N is equal to 4, I have 4s, 4p, 4d, and when n is equal to 4, I pick up my last type of subshell. And I'm going to go all the way to 7, and I'm going to stop at the f's. And I'm trying to make these columns. So part of the trick of getting a good arrow diagram is making sure you have your lines and your columns okay. So I have 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, 7s, 7p, 7d, and 7f. Cool. Well, we don't have any arrows yet. So here are the arrows. They are diagonal. And they run at a kind of 45-degree angle. Okay. So here's my arrows. They run through subshells. So there's my first arrow. My first two arrows only pick up one subshell. My third arrow gets exciting. I pick up two subshells. And then hopefully by then you kind of see the diagonal. And then I pick up two subshells here, pick up three subshells here. Sometimes I'm like, am I drawing this right? Oh, I think it's going to be fine. Now, the arrow has a beginning and the arrow has an end. The way you do this is you complete this arrow, and then you go on to this arrow, well, duh, right? And then you go on to this arrow, and then you go to the top and you go to the bottom of this arrow, the top and the bottom of this arrow, with regard to filling that particular subshell. So you can see in this pattern that actually I'm going to go 3p, 4s, before I go to 3d. The cool thing about each one of these arrows is, and I don't know, you can go back and convince yourself of this, but each one of these arrows has a certain n plus L value. The n plus L value of 1s is 1. The n plus L value of 2s is 2. The n plus L value of both of these subshells is 3. N plus L value of both of those is 4. All three of these have an n plus L value of 5. These three have an n plus L value of 6. These four have an n plus L value of 7, 8, 9, and 10. So that's the arrow diagram, and it gets you where you need to know which electron, where to put the electrons next. So notice that the G's, H's, and I's are grayed out because we don't need to put electrons in those subshells as long as those electrons are in the ground state. And these are the arrows that I drew. Okay, so again, able to draw this for your unit exam a week from tomorrow. So let's see how that will work. We're going to use this arrow diagram to our benefit to do some problems. Oh, by the way, this is actually, I think how Tro does it maybe. It just seems, it's similar, but I don't like it well. I don't have to. Okay, so I could pick any element, and I may do this Wednesday, bring a pair of dice and roll the dice and see what atomic number we get and come up with how electrons are configured around and adding that type of element, as long as it's neutral. Its electrons will be equal to its atomic number. So if we pick on potassium, potassium's atomic number 19. Okay, so one of the things we know is we need to find homes for 19 electrons. Let's see what this would look like. Well, so I told you we're going to start with this first arrow and fill it up. And by the way, we're going spectroscopic notation, not box and arrow, okay? So 1s2, where the first 2 electrons go, and then 2s2, where the next electrons go. Now I'm on my third diagonal, at the top of my third diagonal. Oh, by the way, I've only got 4 electrons on my way to 19. Gotta keep going. 2p6. Okay, now, anytime in your configuration you end up with an NP6, in this case a 2p6, you've probably reached kind of a nice point in your electron configuration. Actually, you have reached a rare gas. And we've talked about this before. That would be what? 10 electrons, that would be neon. Here in a little bit, I'm going to show you that you can actually do what's called an abbreviated rare gas notation, where you can put neon in brackets. But for now, let's just recognize rare gas. All right, now on to 3s. We're going to go 3s2. And now we're going to go 3p6. But this is all consistent with what we talked about last week, in that any p-type subshell, because it has 3 orbitals, you can completely fill it up with 2 electrons in each orbital for possibility of 6 electrons. So now we have 10 plus 8. You're looking at what, 18 electrons? Argon, a pirate's favorite element. Okay, and again, if you've drawn this arrow diagram correctly as a tool, you know that you need to go to 4s next. So we'll go 4s2, then things get, sorry, oh darn it, why? It's not 4s2 because we only needed 1 more electron. So we have 18 electrons here, we're on our way to 19. Sorry about that. All right. So I'm going to show you this on a later slide, but I've been getting ahead of myself all morning long, so why not one more time? We could actually also write this 19 electrons like this, where we put argon in brackets, Ar. We know that's 18 electrons. Those are what we would consider your core electrons. And then beyond argon, it would be 4s1. So my point here is either this or this would be perfectly great. So you just gotta make sure you're doing that. That's called abbreviated rare gas notation. Let's do another one. So we're on our way to, so we did potassium, and actually now we're on our way to zirconium. So I'm sure you buy this, that all of the blah, 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 blah we did to argon is going to be the same for zirconium, and then we just have to do these other electrons. So here we go. The first 2 electrons go in the 1s subshell, so 1s2. The next 2 electrons go in the 2s, 2s2. Then we put 6 electrons in the 2p, so that's 2p6. 2 electrons in the 3s, so that's 3s. Oh, sorry, we've arrived at a rare gas. Here I have my slides, rare gas neon. The next 2 electrons go in the 3s, and you can only put 2 electrons there, so 3s2. The next 6 electrons go in the 3p, so 3p6, and we have arrived, dun dun dun, at argon. 18 on our way to 40. So the next 2 electrons are going to go in the 4s. So 4s2. And remember that any d-type subshell can accommodate 10 electrons. So sometimes students, when they're covering this topic, will go ahead and at the top they'll write you max out at 2 electrons, these p's max out at 6 electrons, these d's max out at 10, and these f's max out at 14. Now you may or may not need to entirely fill them, okay, but anyway. So we have 3d10, so 12 plus 18, you've only got, wait a minute, well, that's getting close, isn't it? $12 plus 18 is 30? Okay, we still got a ways to go. So it's 30, we still need to find homes for 10 more, so we need to go ahead and put the next 6 in 4p. So 4p6. We have come to a p6, so that must be actually the rare gas in the period underneath argon or krypton. So if we add up the superscripts, you're at 36, on our way to 40. So I like the arrow diagram because we left off at 4p. We need to go ahead and finish that. So it looks like we're going to go ahead and put 2 electrons in the 5s, so 5s2. Now we need to go ahead and go on to the top of the next arrow, which is 4d, and we only need 2 more, right? So it's 4d2. And on Wednesday, I'm going to kind of show you how you can look at the periodic table to kind of know how this is. So, kind of like what I said with potassium, we can write an abbreviated rare gas notation, and it would look like this. We would base it upon krypton, and we'd go ahead and put Kr in brackets, and then beyond Kr, we would put 5s2, 4d2. That'd be perfectly legit. Notice the green says in order of filling, and filling using the arrow diagram, which is a reflection of the lowest n plus L rule. So in the order of filling, using the lowest n plus L rule. So there are times when you would want to actually kind of rearrange them. So this is what we came up with. This is how those 40 electrons around the zirconium atom are configured. Notice that if we want to do increasing n, it's going to be one of these where I'm going to move this whole subshell, maybe a 4s this way, and the subshell of 5s this way, along with its electrons. So we could rewrite it in order of increasing n, and it would look like this. Should I write that down because I already have that? Okay, I'll say it. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, I feel like I'm playing bingo, 4s2, 4p6, 4d2, and then 5s2. So the electrons are in the same subshells as we came up with them using the Aufbau method and lowest n plus L rule, but now the whole subshell is in order of increasing n. All right, let's do one more. Let's go around the room. We got 3 now. Let's go around the room. Okay. So, Gabe, where do the first electrons go? How many are there?
1s2.
Perfect, 1s2. So, RJ, where do the next electrons go?
2s2.
2s2. So, what do you think, Cole? Where do the next electrons go?
2p6.
2p6. Back to you, Gabe.
3s2.
3s2. Very good. On to you, RJ.
That'll be 3p6.
3p6. I'm liking it. So we have another rare gas. So we're 18 electrons on our way to 53. So where do they go next, Cole?
3p.
Nope, you got to finish the.
Arrow, yeah. 4s2.
I'm liking it. 4s2. Cool. Gabe?
3d10.
3d10. RJ?
4p6.
4p6. Rare gas. Okay, krypton. So 36 on our way to 53. So Cole, where next?
5s2.
5s2. Gabe?
4d10.
I'm liking it. 4d10. RJ?
5p6.
5p6. Oops. Oh, darn it. It got me too. Oh, got me before. Do you see why it's 5p5 already?
Yeah, because, it's 53.
Yeah, it's 53.
So it would be,
And we can see that, like, it's one away from, yeah. So this is all making sense. Good job, guys. We only needed to accommodate 5 more electrons behind the 10 we put in the 4D.
So are the arrows between the numbers there for the elements, or are they pointing at a specific number?
These right here, these red boxes,
Yeah.
they're showing you that at this point, anytime you reach, put 6 electrons in you've reached a rare gas. You basically have reached the end of a period. So that's a rare gas. So this says in order filling. Let's go ahead and unscramble them. Whoosh. Unscrambling them. Do you want me to call this out? You guys have this one. Unscrambling. You ready? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And then for 4, we have 4s2, 4p6, 4d10. And then we kind of peter out with n is equal to 5. We have 5s2, 5p5. So yeah, like if I help do the whole dice thing, this could be good or bad with having to come up with electron configuration. That's 53 electrons. So I've been talking about the abbreviated rare gas notation. The way this works is, and when you get practice doing this, this will be even more obvious. And what I show you on Wednesday will be even more obvious. But if I'm dealing with iodine, I'm going to build it off of krypton. So I'm going to put brackets krypton, and beyond krypton, I need to say what other electrons I had. So beyond krypton, and usually I would write it, I probably wouldn't write it like this. Mine usually is KR. And then I probably would put 5s2, 4d10, and 5p5. Same diff. I mean, they say the same thing, but I'm kind of favorable to the order of adding electrons. So it like says the same thing.
I have a question.
Yes, sir.
So on the test, if we have, we're going to put in rare gas notation, which one do you prefer, or it doesn't matter?
It doesn't matter. Spectroscopic notation, you can use abbreviated rare gas or just the whole thing. So my answer keys will have both.
I know, but would you prefer the order of filling or the order
Oh.
of pricing?
Probably do the order of filling.
Okay. So the one that you have in red up there.
Yeah. Oh, yeah. Yeah. This one. This is probably what but I'm usually good at, if you put this one, I'll follow it. So, yeah. There are some disadvantages to going with the abbreviated rare gas notation, and it comes in when you're actually going to an ion, not a neutral atom. I'll try to you might pick that up here when we talk about how electrons are configured around an ion. Okay, so we've been talking about it, but just to kind of make sure we're on the same page, abbreviated rare gases form to say how electrons are configured using spectroscopic notation and the abbreviated rare gas spectroscopic notation. You should always base it upon the rare gas in the period before it. So in other words, I would think it would be wrong for iodine if you went back to argon, put argon in brackets, and did the electrons beyond argon, because it really should be argon. Woo. No worries. Put the symbol of the rare gas in brackets. Okay. And you know that you've kind of reached a rare gas if you end up with NP6 sort of electrons in your configuration. Okay. So I kind of mentioned this at the beginning of class. I'm so excited when I do something clever. But anyway, you have a slide at the end of this part, and it actually has all 7 of these questions. And so I don't want all 7 of the questions for you to do them by Wednesday, but what I do want are those first 3 questions. Trying to give you some juice here. Are there any questions about those questions? So I'll be looking for 50, 52, and 54, and I'll have to decide if I kind of break it up and give you points for this one or points for the next one, or just points for, I haven't decided yet. Haven't gotten that far. Just to remind you though, the box and arrow notation I've been talking about, your author calls them orbital diagrams, and the spectroscopic notation I've been talking about, your author calls them electron configuration. Okay? All right, see you tomorrow for lab, hopefully. Don't get sick or